everybody. My name is Robert Young, and I'm part of Group 1, along with Gabriela Costa and Alex Barra. And I will be presenting today the experiment we'll be conducting next week, which is the refrigeration cycle. And there's just an overall schematic of how it looks in a simple block diagram. So for thermodynamic background, the refrigeration cycle serves to use mechanical work to transfer heat. It involves 4 key processes, and these processes are compression, condensation, expansion, and evaporation. The first process, compression, which is labeled 1 to 2 here, is achieved using a compressor, and this is going to in turn increase the pressure and temperature. For 2 to 3 is condensation. This is done using a condenser, and it rejects heat and condenses the vapor to a liquid. And 3 to 4 is expansion. This is done by expansion valve, and it lowers the pressure and temperature. And lastly, there's evaporation, which is 4 to 1. This is done using an evaporator. It absorbs heat and vaporizes the working fluid. In this case, our working fluid is R134A. Next, all these principles are founded in the first and second law of thermodynamics. We've all seen this before. So it's first law, delta U is equal to your heat put in minus your work output, and then second law, your entropy generated is always greater than 0 and equals 0 for ideal processes. This process we'll be conducting will not be ideal, so we will have to see how that plays into the system. Here's it on a basic pH diagram, as you can see here. Yeah, okay. So from 1 to 2, you're getting your isotropic compression. 2 to 3, you're getting your isobaric heat rejection. 3 to 4, you're getting your adiabatic expansion. And then 4 to 1, you're getting your isobaric heat absorption. And similarly, here it is on a TS diagram. So from 1 to 2, you're getting your isotropic compression. 2 to 3, you're getting your isobaric heat rejection. 3 to 4, you're getting your adiabatic expansion. In this case, it does not look to be isotropic because you're getting a little change in entropy there. But that's what we're eventually going to end up seeing. And then 4 to 1, you're getting an isobaric heat absorption again. So to measure the effectiveness of these systems, we have something called the coefficient of performance, otherwise known as the COP. It's to measure the efficiency of the refrigeration or heat pump system. It indicates how useful heating or cooling is provided relative to work or energy input. For refrigeration cycle, this is equal to the heat of the evaporator over the work of the compressor. And for a heat pump, it's the heat in the condenser over the compressor. This is important because it indicates the efficiency of the system. Higher COPs mean better performance and lower energy consumption. And for heat pumps, the COP is going to be better or greater than 1, which means more heat is delivered than electrical energy will be consumed. So our goals for this experiment will be to primarily heat pump analysis. So this will be the determination of the input or inlet power, as well as produced heat and coefficient of performance for the system. And 2 will be visualizing the process. So we're going to end up making it, I believe, as a pH diagram for the values that will be obtained. This is the overall apparatus of the cycle. This is not the actual one we'll be using, but it's the one that was given to us in the lab manual. So I use it for visualization here. This is the actual model, and it may look really ugly and complex with a bunch of moving parts, but there's really 4 main things here. There's your compressor, which will then, this is your 1 to 2, your compressor, your condenser, which will then be, which will cause your compression, and then it will eventually go to your expansion valve, causing expansion, and after that it goes to your evaporator here. And most of the other things in here are a series of temperature and pressure gauges to see what those are at different points in the system. So the procedure here is pretty straightforward and short. First, we're going to start a TRCDC software. We're going to switch on AB1 and AB2, so the evaporator condenser are operative. We're going to switch on the compressor and set an approximate value of 40%. And step 4 will be done 3 total times. We're going to set the evaporator side heat exchanger flow rate to be 3 first, next 4.5, and then lastly 6 liters per minute. And then for each time we do that, we're going to let the system become stable. And lastly, we're going to shut down the entire system when all required values are found. For each of these flow rates, we're going to find the following values: the cooling pressure on the inlet side of the compressor, cooling temperature at the inlet of the compressor, cooling temperature and pressure at the outlet of the compressor, cooling temperature at the outlet of the condenser, and the cooling temperature at the outlet of the expansion valve. So for our predicted results, work required will optimally equal, for our compression stage, work required will optimally equal the enthalpy change. In reality, this is going to be greater than expected. due to not being reversible and adiabatic. And most of our losses here are going to be due to friction and leakages. And the heat transfer regards to working fluid are anticipated to be positive in the beginning stages, compression and negative in the latter stages. Heat rejection, condensed steam will raise pressure and drop in temperature. Enthalpy drop here can be used to find the coefficient of performance. Energy expansion, ideally there will be no drop in enthalpy, but it will be anticipated because there will be a small, rise due to heat gain during expansion. And then heat absorption, steam will be reheated, and there will be a pressure drop, and enthalpy gain will be caused by resistance to the evaporator and heat transfer. So here's some sample calculations I did for coefficient performance with some hypothetical values that may have been obtained. And here we had a COP for refrigeration was 0.83, which is feasible because for refrigeration you're going to get a COP less than 1. There's my references and any questions. All right, thank you.